Okay, welcome back. So in this third and last part of this session, we'll go over a little bit about optimization, I would say, and then finish this session with an example about the code and how it's all looks like in the stack and all of that. And this is the last session, last I would say theoretical session before we start jumping into some hands-on stuff. So, excuse me. So first thing is compilers do lots of generation. They don't generate the code just at once. What they will probably do is they will run the code multiple times and generate, let's say, better code. So they will, when they do the compilation, they might generate uh, multiple versions of the code in order at the end, let's say, to reach some optimization. So you can think of it, it's trying to do, let's say, generate some code, then generating code again until it finally can optimize the code to the best code, which will be more smaller and more faster. So it might take a couple of iterations to get there. We are not going to discuss this out of the scope of this course to talk about optimization, but at least gives you an idea. Here are also some instructions or an example, which will also probably give you an example of what we are talking about. So look at the instructions move and XOR. They can be used to set EAX registers to 0. So, but XOR is smaller as a code byte than the move instruction. So look at this. If we want to set, let's say, EAX with the value 0, we could do move EAX 0, but the problem, or let's say not the problem, but if we look at the code, it's actually 5 bytes. As you can see here, the code is 1, 2, 3, 4, 5 bytes. While if I do XOR EAX with EAX, that should also give me that should also lead to having EAX with the value 0. That's only 2 bytes. So we here minimize the code with 3 bytes, so it's much smaller. But again, we're not going to talk a lot about optimization, but just to give you an example of how things are going to happen. So let's look at this. So think of these instructions are going to be executed by the callee. And let's assume that the callee is going to make another call to another function called foo, which foo will be like requiring one argument or one integer argument. Now the callee will set its local integer variable, let's say to 7, and then send double its value to foo. Let's just take that as an example. Again, the callee is going to call another function. That function takes one argument and it's an integer, and then that argument will create a local integer variable, and we are going to set it to 7, just an example, but we are going to also double that value and send it where to foo. Let's start. So if you look here, the void callee, which just again what we are talking about here, integer argument 1 takes one argument, integer v1, which is the here defining that we have one variable type of integer, v1 equals 7, so we're defining that v1 equals 7, and then when we wanted to call foo, we want to send double that value. So let's look at the code. We push EBP, move EBP ESP, and now we push the value 0 because we want to create the variable in the stack. Okay, and that variable at the beginning is really, it's not going to be really 0, but let's just think of it like that. It's at the beginning, it has no value, so it's going to be 0 for the local variable. Then what's going to happen is EBP copy the value 7 into where EBP minus 4 is actually pointing to. So where EBP minus 4 is pointing to, we will copy the value 7 into it. Then what EBP minus 4 is pointing to, we are going to copy it where? Into ECX. So we're copying now the value 7 into ECX. But before that, here again, EBP, if we do where EBP minus 4 is pointing to, so we have this location, we stored the value 7 in there. And then in the next instruction, we did what EBP minus 4 is pointing to, copy it into ECX. So what EBP minus 4, which is 7, we copied it now where into ECX. So we copied this into ECX. Now we did add ECX, which is the double the value. So that made now ECX 14. And then we, as you can see here, we have push ECX. So we have 14 being pushed on top of the stack. Then we did the call to foo, and then everything continues from there. Okay. Now, before we continue, let's take a look at the stack's memory. Reminder, this is about Endianness. We talked about this, but this is just a reminder of how the actual byte by byte view will look into memory. So as you can see, this is how the byte by byte will, if we look at the memory, let's say byte by byte, this is how the memory will look like for, let's say, the value 7, because these are here, it's 4 bytes. This is 4 bytes again. That's what we mentioned. But if we look at the byte view, this is how these bytes are going to be represented in memory. Okay. Now let's consider this. This is actually not, let's consider, this is the little endian and this is big endian. Little endian stores the values from the least significant bit first. So we can see this is how the value is actually being stored, while the big endian stores from the most significant bit first. So systems or processors like Intel will use have like their multi-byte values are filled starting from the least significant bit, while in big endian, again, like Spark processors, they will have their value filled in reverse order starting from the most significant bit. So it's going to start this way, etc. Okay, so that's why you need to keep in mind we are, in our case, in our course, we are talking all about Intel, so we will be dealing with the little endian. It's very important to remember that. Okay, but as you can see here, EBP minus 4 here points to this value, while EBP minus 4 here points to this value. But again, this is just a byte by byte level. At the end, it's all going to be 4 bytes, at least on a 32-bit system. So let's go back here, and we can see that the default value 0 that was pushed in the epilogue section was not used. Why we did that? We just did that to save some space for our local variables. So compilers, like in C, compilers do not push a default value. Instead, they reverse the space by moving ESP's register. So the compiler will not actually really store a value. It will reserve that space, which we want, okay, by moving ESP, okay. Also, instead of performing the pop to clean local variable space, we can also move ESP to empty the stack frame. So we can do two things, or the compiler will do two things for optimization. It will move ESP to make space for local variables, okay, and it can also move ESP to clean the variables or the arguments on the stack, okay. So now, as if again, what will happen here is the compiler, instead of, again, if you look, go back and forth. So here we have push 0, but here what happened is sub ESP by 4. So we made 4 bytes of space on the stack now, because, and we now ESP is pointing also on top of the stack. But at that location, ESP here will be empty. So we won't have this value 4 over here. Okay, 14, sorry. Now EBP minus 4, copy 7 into what EBP minus 4 is pointing to. So we copied that value over here. Then what EBP minus 4 is pointing to, copy it into ECX. So we copied 7 into ECX. Then add ECX to ECX. So we multiplied, or we doubled the value, sorry. ECX now became 14. So ECX has 14. Push ECX on the stack, so that we pushed now ECX on the stack. And then we called the function foo to do something. Pop ECX, so if we pop this value, it will be removed into ECX, and then here we are cleaning the stack, because this is how C declaration will work. We are removing this, returning, and then the C declaration will have, if there is another value here, which is 7, it will be cleaned by the caller. Now, ESP will move to reserve space for local variables, like I mentioned in the previous slide. But the space is still not initialized. So the space is still not initialized. Again, memory will not like delete and clear those values. So this is what happens, by the way, any one of you which is who is listening now, watching this video, when we first create a variable in C and we go and print it, we usually get this gibberish data. Why is it gibberish? Because it's probably some value which was on the stack, which we are in that memory location, which we are now printing. So again, this value is not really what's happening. The system will optimize it and will just move ESPs much better than storing that value on the stack. Let's continue. Now, another thing which the compiler can do also to save space and make things faster is replace both move ESP EBP, which is when we restore, we want to the epilogue, and we want to delete the stack frame, and then pop EBP. So we can replace those with one single instruction, which is the leave instruction. So what will happen now is instead of having move ESP EBP and then pop EBP, we'll just do leave. So what leave is actually doing is it's doing the move ESP EBP and then doing the pop EBP. Okay, so again, like I mentioned at the beginning, the compilers read the code in many passes before generating the object code. Okay, now one thing the compiler will do is calculate the needed space for all arguments and like the local variables. Okay, so if, let's say, in our case, foo needed 4 bytes, so it will allocate 4 bytes. And that's why we saw sub ESP was subbed by 4. It was subtracted by 4. Why? Because we only need 4 bytes for the function foo. Okay. Also, the push instruction, push is slow instruction. Therefore, the compiler will reserve the argument space in the epilogue section. Okay, keep that in mind. Push is also not a fast instruction. It's slow. So compilers will use something different, which is usually move. So here, as you can see, what happened. Now we can see that if foo takes 2 arguments, then EBP minus 8 is the first one, and EBP minus 12 is the second one, right? Same as performing push for the second, then the first argument. Okay, so if let's say foo really took 2 arguments, then we will have ESP sub ESP 8 because we need 1 for the first and 1 for the second. Okay, everything else, as you can see here, is actually kind of the same. Okay, except for the move ECX into what EBP minus 8 is pointing to. Let's continue. Now, EBP minus 8, what EBP minus 8 is pointing to is for sure the argument to be passed. But we can replace it with ESP in this case. So this is EBP, minus 4 is this one, and minus 8 is this one actually. Why can we replace this in our scenario with what ESP is pointing to? Because currently ESP is pointing to the top of the stack, and so we can do that. But again, that's not our decision. That's what the compiler will do. So if that was to be replaced, we can do, see here, ECX was copied into what EBP minus 8 is pointing to, while here what we did, the push ECX, we did copy ECX to where ESP is actually pointing to. So again, these are what the compiler or the optimization will be doing. Let's look at the example from our code. Now this code, by the way, could also be seen here. So we could see in this one, the code, if we want to go back. So you can see void my function 1, and then you can see the function with the code. We already saw that, and function 2, which is going to be printing this message. And then we have the main function, and this is what main is doing. If you want to look at the assembly code for each one of them, so this is the code for my function 1 after disassembling it, and same for my function 2, and this is the code for main. Let's go back to our presentation. So here the function, my function 1 requires 16 bytes for the local array. So the local array, the buffer is 16 bytes. Okay. Now str copy requires 8 bytes because 4 bytes for this one and 4 bytes for this one. The pointer, this pointer and this pointer, each one requires 4 bytes. So we need 18 bytes. So what that means, and also my function 2 here, in this case, let's just go with the slide, requires 4 bytes for its argument. It's taking a pointer to a buffer, and that argument is 4 bytes. So this means the compiler made the decision to reserve 24 bytes, which is 18 in hex, which is 16 for the array and 8 for the maximum argument space required. Since this one was used the same, we didn't need to allocate that space twice. We just used it once. So 16 and then 4, which means 20, and then another 4, which means 24. Okay, so that's how the compiler will decide, oh yeah, this code needs 24 bytes because this one is 16 bytes, this one is 4 bytes, this one is 4 bytes, and so on and so forth. Now, if you also, let's say, look at the code here, when let's say we are executing the EIP at the str copy will take two values, which is the source and the destination. So we can see that EBP here, which is pointing here, and EBP minus 4, EBP minus 8, 12, and 16, this is where the buffer is started. So this is the location where that buffer is located at. So that's why you can see here, we are saying load the effective address of EBP minus 16 into EAX. Okay, and then, so this is where our destination is. And then what we did is here we copied that address into what ESP is pointing to. So that's ESP pointing here, so that became the destination. So that's why this code is this way. That's what's happening over here. Okay, if we continue, so by default EBP points to the saved EIP, okay, of the caller. In this example it will be main, and EBP points to the EBP plus 4. EBP plus 4 points to the next instruction, or EIP, or the position where we want to go back. In our case it's main. Okay, and EBP itself is pointing to the saved EBP of main. Okay, which is for the previous function. So EBP, this one is pointing for the base pointer of the main function. Okay, now again, str takes two arguments, destination DST and the source src. So that's all of this is just to prepare all of this on the stack. Okay, now EBP plus 8 is the sent value by the caller main to the callee my function 1. Okay, EBP plus 8, so EBP plus 8, this was the value which we sent. Remember, this program, what it does is takes a string and then it sends it to be printed. So EBP plus 8 is our value, the str, okay, which has been copied where, it was being passed to my function, okay, my function 1. Let's continue. So, and my function 2 here takes one argument, which is x, which actually, if you go back here, we'll see what x is the destination. It's the same thing, destination, which was the buffer, because this is the source and this is the destination. How str copy works. So this is the source and this is the destination. And because the destination is still already on the stack, I just changed it here to make sure you understand that. So x is still the destination, okay, which we are passing where to my function 1. And now here what happens is when we go to my function 2, let's say EIP is at here, what's going to happen here is we can see is EBP plus 8 points to the first argument sent. So EBP plus 8 is the first argument sent to my function 2, which is actually, again, what? It's the destination. Okay, the pointer to the destination, and EBP plus 8 points to the second arguments and so on. But in our case, my function 2 only has 1, so actually this will be irrelevant to that function. Therefore, EBP plus 12 points to an irrelevant location for my function 2. That's what I was saying, because my function 2 only takes one argument, so this is still on the stack, it's still there, but it's irrelevant to my function 2. Okay, now can you guess what is currently saved in EBP plus 12? We already saw that this was the destination and this was the source. So if I just go back a couple of slides, we can see it was actually the source of my string, this one, str copy, the str value. Okay, so let's continue. Now here, this is one quiz I want you to, I'll leave that for you to think about. Now, again, main by itself, okay, is a function. So when we finish executing my function 1, we need to go backward to main and continue execution from there. Again, main is just a function, so it will have a frame will be created for main, a frame will be destroyed after main is destroyed or after main is finished execution, and similar to any other function. Now, what do these memory locations contain? M1, M2, and M3. So basic quiz. If you understood what I was talking about over this when we talked about here, if you understood what these are, then you will be able, if you understood, sorry, I mean the session, all the explanation and the code in here, you will be able to figure out what was in M1, what's in M2, and what's in M3, okay? So I'm going to leave that as a quiz for you to figure out. Now also these instructions, can you also tell what these instructions do? I'm also going to leave that for you to figure out. Just try to trace the program and understand what's happening over here, okay? Just try to trace the program and understand what's actually happening over here. Now, at the end of our session, what we can, let's say, conclusions that we can come up with is, what if we can locate the caller's EIP on the stack and change it using, let's say, a move operation or a move instruction or any other instruction? So if we can locate where there is this value is on the stack, which is the position to where I should be going next after my function finishes, okay? Which is where I should be going next after my function finishes the execution. So if we can figure this out, and what if the new value is a location of another block? So what if the new value, which we put in there, is a location of another block? And what if that other block is actually some harmful code? Again, let's say we manage to locate this where it is on the stack. At the end, what is this? It's an address. So if we manage to locate where that address is, so we figured out where the address is, that's one. Then we managed to overwrite that address with an address to some other location. And now that other location includes some harmful code or some malicious code. That's where exploitation will happen, because we can then, once the function execution finishes, it needs to go back to the stored position, which in our case, we overwrote it with some malicious code. That's what is going to be bad for the user, good for our exploit and for our exploitation. Now, these are other references which we use to create this presentation. I highly recommend you go check them out, especially Zeno's Intro to x86, the assembly course. And yeah, that's all for this video. We now have finished, I would say, the introduction to Memoryland, and now we will start talking more about hands-on stuff and exploiting an application. Okay, so that's all for this video. See you in the next video. Thank you and bye-bye.